Lodestar Solutions Virtual User Group from September 25th, 2015 welcomes David West, who is an IBM Predictive Analytics Technical Specialist.
We're going to dive a little deeper into predictive analytics. My colleague just showed you what I'd call is a very powerful tool, but is kind of a predictive analytics light. And what we have now is something that will give you access to practically any algorithm you can imagine and enable you to build models that can be put into production very quickly and very easily. And I guess the real key to the whole thing is its ease of use. But first, I think we need to figure out what it is I'm going to show you. When we're done, so in 30 minutes, you're going to be able to explain what a predictive model really is. You'll be able to explain why you need predictive models, what's the advantage of using predictive models over business as usual. We'll look for some potential uses of predictive models, because these are all around us, and the more you use models, the more uses you'll find for them. I'll describe a process for creating, deploying predictive models that will help you remain organized and provide some governance around their use. And you'll learn a few new phrases like multilayer perceptron and temporal causal model and cajon, things that will just make you seem so much smarter to your friends. So why predictive models? So let's imagine that I walk into your office and it's 8 o'clock in the morning and I've got a newspaper in my hand. It's today's paper. How much is that worth to you? Probably no more than the face value of that paper. Unless your picture's on the front page, then you might give me a little bit extra money for it. But it's not worth all that much money. If it's yesterday's paper, it's worth even less. But how about if that newspaper is tomorrow's newspaper and it's got the financial section in it? That's going to be worth potentially millions, because the information you have about tomorrow, if it's accurate, is going to provide you with an opportunity to change your investments, to know what is going to happen. And so I like predictive models to something that gives you tomorrow's news today. So that's why predictive analytics. And if you think of yesterday's newspaper, that's really what we're looking at when we build reports and dashboards. If the dashboard is updated in real time, then we're looking at today's paper. But unless we have some sort of prediction, whether it's a forecast or a pinpoint prediction of some particular activity, we really are only looking at old news. So what is a predictive model? Looking at the screen, you see this nice bright red line. That is a predictive model. It's an average. It's showing the average height of the ground above sea level between Atlanta and Charlotte. It's an average. So everybody around us has probably built some sort of predictive model. It's very easy to build to calculate averages, and so we do that all the time. So really, what is the definition then of a predictive model? Oops, did I skip? Predictive model is nothing more than some mathematical representation of an environment, of a system of sorts, a business process, or individual behavior, or even group behavior. But it's a mathematical representation of something. So, let's take a look at a couple of additional examples of predictive models. So, batting average. Any kid who's played baseball knows what a batting average is. So, batting average, you look at at how well a guy hits. The earned run average, a measure of the capabilities of a pitcher, how good they are. We use it to compare different entities. How many rebounds and points per game, if you like basketball. But an average is just a very simple predictive model, and it's used to predict a future outcome based on something that has happened in the past. So if somebody has a batting average of .25, then we expect that for every time they get at bat, every 4 times they get at bat, they're going to hit they're going to get a hit. It's not always accurate, though, and that's one of the problems. So why don't we use averages for everything? Why aren't they the best predictive models? Well, let's consider one of the problems with the first model that we looked at, average height. So if I'm a pilot and I'm trying to fly between Atlanta and Charlotte, and the average elevation of the ground is 637 feet, if I stay 10 feet above that, I should be able to go just fine, right? Well, no, because we have these nasty little things in between, like Stone Mountain and mountain ranges, so the height of the ground gets up much above that. We have variation above and below that average, and it's the variation that averages don't do a very good job of addressing. Trends are also things that averages don't do a good job of addressing. So consider the Dow Jones Industrial Average. It doesn't really show a trend. You may see a line on it, but that doesn't mean that the line is going to trend upwards or trend downwards. It's just a line. Another problem with averages is they only deal with one metric. But most of the systems that we deal with have immense complexity, whether we're talking about purchasing behavior of your customers, employee behavior. These are complex systems, and so there are many inputs that should be considered, not just a single metric. So since I mentioned the Dow Jones, we've got a chart of the Dow Jones. It doesn't tell you which component stocks performed well. It doesn't tell you the trends. You'd have to calculate that from that average. And it only shows history and present value. We don't have any forecast for the future. And what we really need is that future forecast. Consider what has happened with Moneyball. Most people should be familiar with that or familiar with sabermetrics. If you're into fantasy baseball or fantasy football, you understand the impact of statistics. But when I was growing up, every baseball card had batting average on the back. So you knew what the batting average is for every player. If it was a pitcher, you knew what their ERA was. Batting average is a very simple calculation. How many hits do you get divided by the number of at-bats? But what if we compare two batters, one who has a batting average of 250 and another who has a batting average of 250? So for every one time at-bat, or excuse me, every 4 times at-bat, they're going to get 1 hit. But what if the first guy, when he gets at-bat, every time he gets at-bat, he hits a triple? And the other guy, every time he gets at-bat, he gets a single. Which one's better? Well, not all hits are created equal. And so sabermetrics and Moneyball started looking at other characteristics to measure the performance of the batter. So batting average is one mathematical representation of that behavior, but it's an inaccurate one. And so they tried to come up with something a little bit more complex called the WABA, or the weighted on-base average. And it considers each of these different characteristics. For example, the very first factor you see there, NIBB, non-intentional bases on balls, and then hit by pitches, singles, reached base on error, doubles, triples, home runs. It tries to take into account all of the potential ways that a batter can positively impact the game. And then instead of dividing it by the number of at-bats, we divide it by plate appearances. Because in the batting average, you don't consider bases on balls. They don't affect your batting average positively. They don't even count as at-bats. So there's a lot more to it. And so that's the trend. That's the direction we go with predictive analytics. We look for additional characteristics that can be used to describe that system that we're trying to make some prediction about or make some forecast about. So gathering more things, doing things more and more like what a human brain would do. So what we're looking at here is a diagram of a multilayer perceptron. Multilayer perceptrons are a type of neural network model that come out of the machine learning space. Machine learning is an attempt to make software that behaves like the human mind. We're able to consider many different things, whether we're considering sounds that we're hearing or sights that we're seeing. We can perform incredible calculations instantaneously in our heads without even trying. Just try catching a ball. Someone throws you the ball, your brain calculates the trajectory, which normally would require advanced calculus to to account for gravity and wind speed and things like that. But a multilayer perceptron considers many different characteristics. It considers the relationships of those characteristics to each other, makes adjustments for those, and comes out with some outcome. And in this case, we're trying to predict whether or not a customer is going to remain active or is going to go to inactive state. So we're trying to consider as many characteristics and their relationships to each other to predict some outcome. So getting a little complicated, let's take a simple look at things that we should be predicting. I've been working with several customers, a very large soft drink manufacturer and a hospital company who want to predict which employees are going to leave and which ones are going to stay. You don't want to lose good employees, you want to keep them. You might want to lose some of the poorer performers. But if you can predict which of your best employees are likely to go over to a competitor or change jobs, you might be able to find ways of encouraging them to stay, whether it's through a bonus program or something like that. Customer acquisition, cross-selling behavior, so you've got a product you want to sell to your existing customer base. Outcomes for patients. I built a model that predicted the onset of congestive heart failure a couple of years ago in a population of people in Virginia. So you can predict almost anything. The list of potentials is practically limitless, and we're not going to go into all of the details here. But how do we do it? So we've got three different categories of analytics: supervised learning, unsupervised learning, and forecasting. So supervised learning implies that there is some target. We have a target, a metric, a behavior, something that we want to predict. We want to predict, will this customer buy this product? Will this employee leave? Will this patient develop such and such a condition? All right, so that's your target. Because you've got that type of target, you need some historical information that describes what did these patients or customers or employees do in the past? What was their past behavior? And we use that past behavior to predict the future outcome, or predict the target. The end result is we have a score that is related to the probability of the targeted outcome actually occurring. It can also be interpreted as a prediction or recommendation, such as a yes or no. Will this employee leave? Yes or no. It's a lot easier to interpret a Y or an N than it is a 0.881. Does that mean they're staying or they're going? So you can get both from the output. Some of the things that you may have heard about as algorithms, the SVM was mentioned in the previous talk, the support vector machine, self-learning response models, neural nets, regression, lots of different types of decision trees. We're going to see a little bit of that in a minute. So those are the type of algorithms we use. Supervised learning is similar to forecasting in that that forecasting requires a target. So I'm jumping down at the bottom here. Forecasting, though, predicts some metric and is time dependent. So you have something that occurred on such and such a date. Typically, you'll use things that are measured on a regular basis and are smoothed out over time, but that's not always required. Some of the examples would include ARIMA modeling and exponential smoothing, where we're taking the historical pattern of time-dependent behavior for a metric, and we're predicting that or forecasting that in the future. We can account for things like seasonality or cyclicity. There's a regular cycle, whether it's a lunar cycle that affects the behavior or the metric, or it's a seasonal cycle. Attendance at baseball games tends to go up in October. There is no attendance at baseball games in January. That's seasonal behavior. But forecasting accounts for that sort of thing. And then the final category, unsupervised learning. This is where you take a bunch of data and you throw it in. You don't have a target. You're looking for that wow type of insight. We're grouping individuals or records or employers. We're grouping things together based on their similarities to each other or their differences from other groups. You don't need historical information. You're just looking at a snapshot in time. You may apply some history to that, but for the most part, you take a snapshot and you cluster the data. The end result is a cluster assignment for that record. this individual belongs in cluster A. Cluster A is composed of people that spend lots of money and have big seats. It could be totally unrelated things that define that cluster. But the theory is that people that are in the same cluster will tend to behave in similar manners. So we can then apply some other prediction to that cluster and use that to start our analysis. Some of the algorithms that are there for us are k-means, Cahonen, and the two-step algorithm. So now that you know almost all there is to know about analytics, what sort of methodology should we be using? Well, IBM suggests that you use the CRISP-DM methodology. IBM, along with other organizations, created CRISP-DM. It's not specific to IBM. And Kaggle.com, which is a data mining website, did a survey last November and found that 47% of all organizations that conduct data mining use this methodology. It was the #1 methodology used. It begins with an understanding of the business, and presumably that's where you come in. You understand your business. We then move into understanding the data. These two things go hand in hand. The data describes the business, describes the historical patterns, describes your customers, your employees, or whatever it is you're working with. But understanding the relationship between that business and the data is also very important. So once you've understood the data, you know what flaws exist in the data, you know where the data needs to be cleansed, you know that this term changed on such and such a date, and so we have to account for that. Then we move into data preparation. As you prepare the data, you will find that there may be some surprises, and so that enhances your data understanding. So we have this continuous loop going on. Once you've gotten the data ready for modeling, the data typically looks like a nice, wide, orthogonal table, like a great big spreadsheet, like something you'd pull straight out of Cognos. That nice, wide spreadsheet then gets modeled. You look at the model, that may inform you of other things about the data that require additional preparation. So you go back and re-prepare the data, make some changes to it, maybe create new columns, bring more data in, and build a new model. You evaluate your models that you've created, you compare them to each other, and once you've settled on the best performing model, you don't think you're going to get any better for one reason or another, then you deploy the model, and that's where you get the money. The money comes from actually deploying the model. Doing the esoteric exercise of creating models doesn't help until you actually deploy it. When you deploy, there are lots of different ways of doing it. You can create a process that scores your incoming data. Maybe you've got a database of potential customers. You score that database and it comes up with prediction for which customers are likely to respond and which ones aren't. So now you've got an actionable table that you can use to drive your sales activities or your employee retention activities and things of that nature. If you're talking about a real-time process, maybe you're scoring data on people that come to your website. When they hit your website, they log in, they're instantly scored based on their click path that led them to the site and some prediction about what pop-up offer could be presented. All of that are different ways of deploying. So you've got batch deployment, you've got interactive deployment, you've got real-time deployment. So all of those things go hand in hand. But this is a constantly evolving pattern. My colleague mentioned that as you apply your model to the data and you take action on it, that information can be put back into the data, and that will improve subsequently created models. Pretty straightforward stuff there, right? All right. So now what I'm going to do is, in 5 easy steps, we're going to build a predictive model. So we have some banking data that shows which customers responded to a specific offer of a product. And we want to predict which future customers are likely to respond. Pretty straightforward stuff. So I'm going to turn off PowerPoint, and I will fire up Modeler. Back over here. And there we have it. Can you still see my screen?
Sure can.
Great. Okay, I worried there. All right. So the first thing we're going to do is over on the right-hand side, we see that we have our CRISP-DM process outlined, beginning with the business understanding. This is a software product. If I had notes, I could embed them here in my CRISP-DM process under business understanding. I don't. So we're moving straight into data understanding, then we'll prepare the data, we'll then model the data, we'll then evaluate the models, and then we'll deploy a model. Now it begins with some data. We can pull data directly out of Cognos. I don't happen to have any data in Cognos right now that I can pull in. So I'm just going to read from a flat file. We can read from practically any data source. Whether you've got data up in Salesforce.com, you want to read that dynamically, you want to pull it out of Netezza, we can pull data out into Netezza, and we can push modeling into Netezza. So there's a great deal that can be accomplished using Netezza or DB2 or any database for that matter. But we're going to start out by pulling in our bank response data. Just drag that right here. And we can see right off the bat that we have some columns in the data. We can filter them, turn them on and off. We see what type of data is being brought in. If I want to preview that, now I can see just the first 10 records. I can adjust that if I want to see more, but I see exactly what I've got. Some customer information, a unique identifier for each customer, describes their household, describes past purchasing behavior and whatnot. And then we have an indication of their response to a previous campaign. So 0 means they didn't respond, and 1 would mean that they did. All right. Now my next step is I need to instantiate our metadata. And so we connect this. We've instantiated metadata, so we now see what are for the continuous variables, those are our numbers, what's the min and max. So I can at a glance determine, is there something wrong with the data? And I do see that month's current account has a negative number as the minimum, which implies that there might be something that I'd have to do with that. But since we're just doing a quick demonstration, I'm not going to worry about it. Our response we're going to set as our flag, or as our, as our target, and it is a flag variable. It's a 1 or a 0. Some people refer to it as a binary. And then we've got a record ID, so that is our customer ID. Pretty straightforward stuff. Now, to understand the data, I need to do an audit on that data. So we'll connect that and then run my data audit. And very quickly, we can see the distributions of values of all of our numbers. We see the distribution of our target or our response field, and it looks like it's very low. Well, let me take a quick run on that, and I can see that only 3.7% of our customers responded to our offers. That tells me that I'm going to have to make some modifications to the data. I could very easily make a model in my head right now, and so could you if you think about it. That would be 96.3% accurate. I would predict that no one's going to respond to any of our campaigns, and I will be right 96.3% of the time. Of course, I'll miss those 3.7% of the people who would actually respond. So we need to do something to enable our model to be created. So I'm going to generate a new node called a balance node. We'll close that, and I have this new balance node that has appeared here. And that calculates that for every non-response, it's going to oversample the responders by a factor of 26, and that will result in an approximate 50-50 distribution of responders to non-responders. Pretty straightforward. As a best practice, connect that. We also need to partition our data. Now, you can make an argument over whether we should partition it before or after the balancing, but we won't go into that at this point. Best practice for partitioning simply implies that you're creating a holdout data set. I'm going to build my model with one data set. I'm going to compare it to the performance of another data set that has been held out. If the numbers come out roughly equal, then we conclude that the model is generalizable to the overall population. If they don't, then we need to go back to the drawing board. And that's the whole purpose of that. So now our data is prepared. It's going to be divided into 2 data sets. It's going to be balanced. We've got our target defined and whatnot. So now we want to model it. Now, in the previous presentation, we saw a decision tree. We heard support vector machine mentioned. I've already mentioned Multilayer Perceptron as a neural network model. But I'd be willing to bet that nobody on this call can tell me what is the best model or best modeling algorithm to use to predict response in this case. And the fact of the matter is, nobody would know. You just can't know. You have to try different things. Now, if you're someone who loves regression, you're going to miss out on a lot of potentially better models if all you ever do is regression. So the idea here is to do an automatic process that enables you to compare the performance of multiple modeling algorithms, whether you're talking the C5, a decision tree algorithm, logistic regression, decision lists, Bayesian networks, discriminant analysis, and so on. All of these different things are available at our fingertips. And when we run that, I'm not going to run it right now, but when we run that, we end up with a model. And that model, in this case, is going to be the best of three different models. We have a discriminant analysis, logistic regression, and a C5. And the overall accuracy is not great. It's our first step, 74, 72, 57. By using this auto classifier node, we have a model that is going to combine the results of all three of these models into what we call an ensemble. And that ensemble oftentimes will have better performance than just a single model by itself. We can look at the actual model. I'll pull up the C5, see what they look like. A C5 is just essentially a bunch of if-then-else statements. We can view the model itself, and you see that we've got a nice decision tree that filters out based on a whole bunch of different rules that it has essentially created. All right. The next thing we need to do is evaluate which model gave us the best performance. And I'm going to connect these, and we'll run these simultaneously. And there we have it. So the first thing is our gains chart, and we see we typically look at the gain at about the 30th percentile. And what we're looking at is our decision tree, our C5, and our logistic regression color-coded here. And then the XF response is our ensemble model. And we see that the ensemble model has much better performance than the component models. So that's a good thing when our ensemble does better. We can see the raw numbers here, and we see that looking at comparing the training to the testing data set, the numbers are fairly close except with the C5, so we might want to kick out that model. It's not all that great anyway. It's overfit at the beginning. But for our ensemble, it looks pretty good. Now, how do we get anything out of that? Well, we want to deploy the model. And the way we deploy the model is to take the model and just connect it straight to our data. Now, this could be, we could connect this to an incoming brand new data set that was unrelated to this, perhaps just a customer database of new customers, and you run them through the model like this. Oops. Give me just a second. There we go. And the end result is we have our predicted response. We have the confidence in that prediction. So a very high confidence would indicate that it's a very strong propensity for them to not respond. The lower the confidence, the lower the likelihood that they will respond. We could then take this, further subset it very easily. I'll just select, connect that in line, and the predicted response is equal to and we've got our predictions. There you have it. So we've got our predicted responders, along with their confidence, we can adjust our interpretation of this. We only want the cream of the crop. We only want those who have a predicted response propensity or response confidence that is higher than a certain threshold. By default, it's going to take anybody here that has a prediction of 1. This data, although I created it in a table, could be very easily exported straight back out to Cognos. Just like that. Could be written out there. It could be written any place. So what we've just seen is a very quick and easy way to create models following the CRISP-DM methodology using SPSS Modeler. We brought our data in. We explored it a little bit. We verified the distributions of it. We did some minor data preparation. There's a lot more that we can do. We built a number of different models, including an ensemble. We evaluated the performance of those models, and then we deployed the model. This whole stream, what we call a stream, is then stored as a flat file, a .str file. That str file can be kicked off to run in batch. It can be deployed as a web service so that it can facilitate real-time scoring. So pretty straightforward, simple process. I hope you see how easy it is to actually build a model that can be useful. At this point, I'll open the floor to questions.
Thank you, David. That was extremely enlightening. I enjoyed seeing how quick and easy you can do it in 5 steps. I think it's I think it's great. How does someone get started? How would if there's somebody out there looking or thinking about predictive, where do you think they start? What's the best approach to start this? Because it's a completely different process compared to, as you said, the BI, the dashboards is all yesterday's news. How do you start thinking about tomorrow's news?
Well, I think the first thing is to identify a potential use case. Where is it that a better prediction is going to help you? Where do you have a problem? Do you have a problem with customer acquisition? Do you have a problem with employee retention? There are literally hundreds of possible use cases for it, but identify that use case and go after the low-hanging fruit. Once you've found that use case and you've demonstrated some initial success, that gets the powers that be to sit up and take notice. Then they'll be willing to spend even more money to expand your capabilities for building predictive models, for deploying predictive models, and for leveraging the data that you already have so you can put it to work for you.
Yeah, absolutely. Because a dashboard, in most cases is old, right? It's hard to take action on it because it's already happened.
That's right.
Yeah,
that's right.
Absolutely.
Now we only scratched the surface on the different types of models. I talked about supervised learning, which is what we just went through. I talked about forecasting. We haven't done that. I've talked about clustering, and we didn't do that. But that's all possible within this interface. Other things that are possible here, manipulating the data. Let's say you've got 10 different tables that need to be combined in order to build your model. Well, that can all be done from a single interface. You don't have to jump out to some query management system or whatever. We can do it all in one interface, and you end up with a process flow that shows all your inputs. Doesn't matter if it's in a database or if it's a flat file or both. We can pull it all together. One-stop shop for preparing the data, modeling it, and deploying it.
Excellent, excellent. I don't think there are any other questions. I want to thank you for your time. Oh, Heather, do you
I have one question. This is Heather. So my question for you, David, is a lot of our clients that we start to talk to about predictive and how do you get there, they always come to the question, they're like, well, we don't have a data scientist. What would you suggest, what would your response be to those clients that still, after seeing all this, think that they need to have that data science background, a PhD in stat and so forth? How can you, what insights can you share for them?
Well, when I started building predictive models, I was an underwriter. I wasn't a data scientist. What I brought to the table was a very solid understanding of the business. And I think that's the most important thing to have as a foundation is you need to understand the business. The understanding of the data comes later. Using a tool like this can enable you to better understand the data. You're going to need to work with your DBAs or people that know the data structures, but you can learn from them. You don't have to have a PhD in statistics to build predictive models. You don't have to be a formal data scientist to build predictive models. What you really need is a willingness to explore, an understanding of the business. The rest will fall in line.
I guess responding to some of the points that David was mentioning as far as predictive analytics, one of the things to keep in mind is that the modeler engine, when we talk about the offerings on the IBM offerings for predictive analytics, it runs the entire spectrum from data collection through management, analytics, and then finally reporting and deployment, as David was pointing out. Modeler is specifically designed. I think the question was how much ramp-up time, how much education. Remember that Modeler is specifically designed for the business user in a way similar to Watson Analytics. But Modeler, of course, predates Watson Analytics, and it's designed for the business user to answer business questions from within that crisp DM methodology. So when you think of applications like SPSS statistics, that's an engine that is principally designed for a sort of top-down approach. I have a hypothesis and I want to test it. Modeler, on the other hand, takes data mining and predictive analytics one step further in a bottom-up hypothesis generation approach. And where we contextualize Watson Analytics in that spectrum to complement both SPSS statistics and SPSS modeler, IBM SPSS modeler, is effectively Watson Analytics is that tool to guide the analytic imagination, and then go to the data scientists, the business analysts armed with statistics or armed with modeler, and say, I've got this very interesting idea. I see something in the data is boiling to the top. Let's use the crisp DM. Let's use data mining techniques. Let's use modeler to corroborate those observations, corroborate the responses. And so in answer to the idea of how much training does it get, David's right on target with, first of all, identifying those business problems. And then once the business problems have been identified, it then becomes much easier to tackle, especially when you consider that those engines are principally designed for the business user to solve business problems. And I hope that lends sort of color commentary.
So, John, would you say that if they're really starting from ground zero, that they could use the sticky note exercise that I was just mentioning about to actually just even start brainstorming where to start looking, even using a Watson or an SPSS?
I'd say certainly so. Remember that oftentimes if we're starting from ground zero, if we really don't know where we're going, a hypothesis testing approach is sort of like putting on horse blinders without really even knowing where the path has taken you. When we allow, we go through that brainstorming exercise, we find out what the business problem is, and I remember in grad school, our committee kept telling us, refine, refine, refine. And when we finally have that business problem, with metrics to measure, and actually if we don't even know if we have the metrics, this can range, and IBM SPSS solutions, business intelligence solutions to include the Cognos suite of applications. We can also interrogate structured data, look at social media and find out what's there, gather that information, interrogate what sentiment is there, connect that with other structured metrics, and then allow those patterns that are resident in the data basically illuminate themselves. And Modeler is principally designed to do exactly that. When we use that then in context with Watson Analytics, Watson assists the analyst, sort of directing the attention, that guided analytics, to come up with these insights and say, hey, data scientist, hey, statistician, IT guy in the back room, now I've got this insight. I really need to standardize this. I really need to corroborate this, and I think this can help our business when put or deployed, as David was mentioning. We can deploy this in our everyday business processes and thereby really affect the business.
Great advice. Any other questions, Mike, on the screen there?
Nope. That is it. That's a great question, by the way. All right.
Well, thank you so much, David. This is very impactful. I learned a lot, actually. So thank you for your time.
I'm glad to do it. Thanks for having me.